You are looking at a galaxy through the infrared vision of the James Webb Space Telescope, and it appears as a bright, concentrated cluster of light with structure visible within it. The galaxy shows a defined shape with what looks like spiral arms or a disk formation, and the brightness suggests an enormous number of stars shining within this system. The color in the processed image appears reddish and orange because you are seeing infrared wavelengths that your eyes cannot normally detect. Wavelengths that have been shifted by the galaxy's tremendous distance. This galaxy contains hundreds of billions of stars, and the light you are observing left this system when the universe was only 300 million years old. The structure you can see through JWST's instruments shows organization and maturity, features that normally develop over billions of years in galaxies closer to our own time. Spiral arms curve outward from a bright central region, and star-forming areas appear as brighter knots distributed across the disk structure. The galaxy appears fully formed, with distinct regions of different brightness, and the overall appearance resembles galaxies in the modern universe, despite the enormous difference in cosmic time. The total mass in stars appears to be somewhere around 100 billion times the mass of our Sun, a value that rivals the largest galaxies we see in the nearby universe. You are listening to the Drowsy Astronaut, and tonight we are exploring one of the most surprising discoveries from the James Webb Space Telescope. A journey through the early universe where galaxies appeared that seemed too massive and too mature to exist so soon after the Big Bang. This will be a slow and unhurried exploration of those distant galaxies, the light they sent across billions of years, and the questions they raised when they finally came into view. If you are still awake later, feel free to share in the comments where you are listening from. And if this kind of content helps you learn and rest, consider liking the video or subscribing to join us for more journeys through the cosmos. Looking at this galaxy in the JWST image, you can see that it sits among thousands of other galaxies scattered across the deep field of view, each one appearing as a small smudge or point of light. This particular galaxy stands out because of its brightness and because of the redshift measurements that place it at an extreme distance. The image was captured using JWST's near-infrared camera, which observes wavelengths from about 0.6 microns to 5 microns, wavelengths longer than visible red light. These infrared wavelengths are crucial because they allow JWST to see light that has been stretched by cosmic expansion during its journey across billions of light-years of space. The galaxy appears clearly resolved in the image, which means JWST can see structure within it rather than just a point of light, and this resolution reveals information about how the galaxy is organized. The central region appears brighter than the outer regions, suggesting a concentration of stars toward the center, similar to what we see in mature galaxies. The disk structure, visible in the image, suggests rotation with material orbiting around the galactic center under the influence of gravity. The overall diameter of the galaxy appears to be about 20 to 30,000 light-years across, roughly a quarter the size of our Milky Way, but containing a comparable number of stars. Multiple filters were used to capture this image, with each filter allowing light of specific wavelengths to pass through to the detector, and combining these filtered images creates a detailed view of the galaxy's appearance. The reddest filters show the galaxy most prominently because most of its light has been shifted into the longer infrared wavelengths. Filters that observe shorter wavelengths show much less light from this galaxy because cosmic expansion has shifted that light away from those wavelengths. The pattern of brightness across different filters provides information about the galaxy's distance, stellar population, and physical properties that can be analyzed to understand what this object actually is. The brightness of this galaxy in the infrared wavelengths indicates a large population of stars generating significant amounts of light. And the total luminosity suggests active star formation or a large established stellar population. Stars produce light through nuclear fusion in their cores, and the amount of light a galaxy produces correlates with how many stars it contains and how old those stars are. Young, hot stars produce more light per unit mass than older, cooler stars, so the brightness alone does not immediately tell you the total mass. But the combination of brightness, color, and structure provides enough information to estimate that this galaxy contains a stellar mass equivalent to roughly 100 billion suns. Looking more closely at the structure, you can identify regions that appear slightly brighter than their surroundings, and these likely represent areas of active star formation where new stars are being born from collapsing gas clouds. Star-forming regions produce intense ultraviolet light from hot young stars, and although this ultraviolet light has been redshifted into the infrared by the time it reaches JWST, it still creates bright spots in the image. The distribution of these star-forming regions across the galaxy's disk suggests ongoing activity rather than a galaxy that has already finished forming all its stars and settled into a quiet state. The galaxy sits in a region of the deep field that also shows other high redshift galaxy candidates nearby, and the clustering of these objects suggests they are part of the same large-scale structure in the early universe. Galaxies tend to form in groups and clusters because they arise in regions where dark matter has concentrated and created gravitational wells that attract normal matter. The presence of multiple massive galaxies in the same region of sky indicates that this area corresponds to an overdensity in the early universe, a place where structure formation was particularly active. These neighboring galaxies appear smaller and fainter than the main galaxy you are observing, which suggests this particular system is among the most massive in its neighborhood. The clarity of the image demonstrates JWST's extraordinary sensitivity and resolution, capabilities that were specifically designed to enable observations of the earliest galaxies in the universe. The telescope's primary mirror is 6.5 meters in diameter, much larger than Hubble's 2.4-meter mirror, and this larger collecting area gathers more light from faint, distant objects. The infrared optimization means JWST can see the redshifted light from high redshift galaxies that would be invisible or extremely faint in visible wavelengths. The cryogenic cooling of the instruments reduces thermal noise, allowing detection of extremely faint infrared signals that would otherwise be drowned out by the telescope's own heat radiation. Observing this galaxy required pointing JWST at a specific region of sky for an extended period to collect enough photons to create a detailed image. And the exposure time for deep fields like this, one can range from tens of hours to over 100 hours of total integration. The telescope must remain precisely pointed at the target, despite orbiting the Sun at the second Lagrange point, located 1.5 million kilometers from Earth in the direction away from the Sun. The stability and precision of JWST's pointing system allow it to collect sharp images of objects that appear incredibly small on the sky, with this galaxy subtending an angle of less than 1 arcsecond. The galaxy's appearance in this image closely resembles what we might expect from a mature galaxy billions of years old, and therein lies the puzzle that makes this discovery so surprising. Galaxies require time to form their stars, develop structure, and settle into organized configurations, like the disk or spiral pattern visible here. The processes of star formation, stellar evolution, and galaxy assembly all operate on specific timescales determined by physics. When the universe was only 300 million years old, theoretical models predicted that galaxies would still be small and irregular, having had insufficient time to grow to the massive, organized states we see in later cosmic epochs. Yet here is a galaxy that appears to defy those expectations, showing both enormous stellar mass and structural maturity at a time when such objects should not yet exist according to pre-JWST models. The stellar mass of roughly 100 billion solar masses is comparable to the Milky Way's stellar mass, but the Milky Way has been accumulating stars for over 13 billion years. This early galaxy appears to have assembled a similar amount of stellar mass in only 300 million years, requiring a star formation rate and assembly efficiency that seems implausibly high based on previous understanding of galaxy formation. Looking at the spectrum of light from this galaxy, if spectroscopic observations are available, would reveal emission lines from elements like hydrogen, oxygen, and other species that can be used to confirm the distance and study the galaxy's properties. Spectroscopy disperses the galaxy's light into its component wavelengths, creating a spectrum that shows bright emission lines at specific wavelengths corresponding to atomic transitions. These emission lines appear at wavelengths shifted from their rest frame values by the redshift, and measuring this shift provides a precise distance determination. Some of these early massive galaxies have been confirmed spectroscopically, while others remain photometric candidates, awaiting detailed spectroscopy. The discovery of this galaxy, and others like it, in JWST's first year of observations, has prompted intense scientific activity and debate about what these objects reveal about the early universe. Initial reactions ranged from excitement about seeing the early universe in unprecedented detail to puzzlement about how these massive systems could exist so early. Some researchers questioned whether the mass estimates could be correct or whether the redshift measurements might be systematically wrong, placing these galaxies at less extreme distances, where their masses would be less problematic. Others began exploring whether galaxy formation theory needed significant revision to account for more rapid early growth than standard models predicted. The galaxy sits in the deep field image like a time capsule, its light carrying information about conditions in the universe when the cosmos was less than 3% of its current age. Everything you can see in this image represents the galaxy as it existed 13.5 billion years ago, frozen in time by the finite speed of light. The galaxy itself has continued evolving over all those billions of years since this light departed. And if you could somehow see it as it exists today in real time, it would look completely different, having aged and perhaps merged with other galaxies or evolved into a massive elliptical system. But JWST allows you to look back through time and observe the galaxy as it was during cosmic dawn. The image you are viewing represents one of the deepest and most detailed views of the early universe ever obtained, revealing galaxies that existed within the first few 100 million years after the Big Bang. This capability to observe cosmic dawn represents the fulfillment of JWST's primary science objectives and the realization of decades of planning and technological development. The surprise of finding massive, mature galaxies so early was not anticipated before launch, but it demonstrates that JWST is working better than expected and revealing aspects of the early universe that remained hidden from earlier telescopes. The galaxy glowing in infrared light before you is one of these revelations, and understanding what it truly represents requires exploring the journey its light took to reach the telescope. The light you are observing from this massive early galaxy has been traveling through space for over 13 billion years, and understanding this journey helps explain both how we see the galaxy and why its existence is surprising. Light moves at 300,000 kilometers per second, the fastest speed possible in the universe, and nothing with mass can travel at this speed or exceed it. This speed seems impossibly fast on human scales, with light capable of circling Earth's equator 7.5 times in a single second. But on cosmic scales, even light takes a very long time to cross the enormous distances between galaxies, and the light from this galaxy has been in transit for most of cosmic history. When photons left this galaxy 13.5 billion years ago, they began a journey across expanding space that would take them through the evolution of the entire universe. The universe at that time was much smaller, denser, and hotter than today, and the expansion of space itself has continued throughout the photons' journey. These photons have passed through the epoch when the first galaxies were forming, through the period when galaxy mergers and growth created larger structures, through the formation of our own Milky Way galaxy, through the birth of our solar system 4.6 billion years ago, and through all of Earth's history, including the evolution of life. The photons finally reached JWST's mirror in 2022, delivering information about a galaxy that existed before any of these later cosmic structures were present. The distance to this galaxy is often stated as 13.5 billion light-years, which represents the look-back time or light travel distance, the time that light has been traveling. This means you are seeing the galaxy as it appeared 13.5 billion years ago, and the universe was only about 300 million years old at that time. But the actual current distance to the galaxy is much greater than 13.5 billion light-years, because space has been expanding during the light's journey. The expansion of space continuously creates more distance between objects, so the galaxy is now farther away than it was when the light left it. The current proper distance to this galaxy, accounting for the expansion that occurred during the light's journey, is approximately 30 billion light-years, or possibly even more, depending on the exact cosmological parameters. This means that if you could somehow freeze the expansion of the universe right now and measure the distance to where the galaxy currently is, you would find it at this much greater distance. The difference between light travel distance and proper distance is one of the subtle aspects of cosmology that emerges from living in an expanding universe. The expansion doesn't mean galaxies are moving through space away from us, but rather that space itself is stretching and creating more distance between objects. Looking at the path the light traveled, you can think of it as a straight line through space, from the galaxy to the telescope. But this line exists in expanding space, which means the geometry is more complex than simple Euclidean geometry. The photons experienced the expansion of space as they traveled, and this expansion stretched their wavelengths continuously throughout the journey. Light that left the galaxy as ultraviolet radiation, with wavelengths around 100 nanometers, arrived at JWST as infrared radiation with wavelengths around 1 to 2 microns, stretched by a factor of 10 to 20. This stretching is redshift, and it is the key observational signature that tells us how far away and how long ago we are seeing when we observe distant galaxies. The photons traveled through an evolving universe, and the expansion rate has changed over cosmic time due to the changing balance between matter, radiation, and dark energy. In the early universe, radiation and matter dominated the energy density, and expansion was decelerating as gravity pulled back against the initial expansion from the Big Bang. Later, as the universe expanded and matter density decreased, dark energy became increasingly important. And about 6 billion years ago, the expansion began accelerating. The photons from this early galaxy traveled through both the decelerating and accelerating phases, experiencing a complex expansion history that determines their total redshift and the current distance to the galaxy. The fact that you can see this galaxy at all is remarkable, and it required the light to travel unimpeded through space for over 13 billion years without being absorbed or scattered too severely. The universe became transparent to visible and ultraviolet light about 380,000 years after the Big Bang, when electrons and protons combined to form neutral hydrogen in a process called recombination. After recombination, photons could travel freely through space without constantly scattering off free electrons. This transparency has persisted ever since, allowing light from distant galaxies to reach us across cosmic time. However, the early universe underwent another transition, called reionization, when the first stars and galaxies formed and their ultraviolet radiation ionized the hydrogen gas that filled space. This reionization happened gradually between about 200 million and 1 billion years after the Big Bang, during the period when this galaxy you are observing existed and was shining. The ionized gas during reionization can scatter short wavelength light, which affects observations of the most distant galaxies. The galaxy you are looking at existed during or near the end of the reionization era, and its light provides information about this important cosmic transition. The photons that traveled from this galaxy to JWST are just a tiny fraction of all the photons the galaxy emitted, and most of the galaxy's light has traveled in other directions across the universe and will never be detected by any observer. The solid angle subtended by JWST's mirror, as seen from the distant galaxy, is extraordinarily small, and only photons traveling in exactly the right direction could possibly reach the telescope. Of the photons that did travel in the right direction, many were absorbed or scattered during their journey, and only a small fraction actually made it to the detector. The image you are viewing was built from individual photons arriving at the detector, accumulated over hours of exposure time until enough photons had been collected to form a clear image. Each photon that contributed to the image carried energy determined by its wavelength, with shorter wavelengths carrying more energy than longer wavelengths, and the total energy detected allows estimation of the galaxy's luminosity. When the photons were emitted 13.5 billion years ago, they had shorter wavelengths and higher energies corresponding to the ultraviolet and visible light produced by the galaxy's stars. The expansion of space during their journey stretched the wavelengths and reduced the energy of each photon by the same factor as the redshift. A photon emitted in the ultraviolet at 100 nanometers with energy around 12 electron volts arrived in the infrared at 1 micron with energy around 1.2 electron volts. The journey of light from this galaxy demonstrates the connection between distance and time in cosmology. And looking at distant objects means looking backward in time to see the universe as it was. This connection exists because light travels at a finite speed, and the farther away an object is, the longer its light takes to reach us. When you look at the galaxy in JWST's image, you are not seeing the galaxy as it exists today, in real time, but rather as it existed when the light left it. The galaxy has had 13.5 billion years to evolve since that moment, and its current state is unknowable through direct observation because light showing its current appearance has not yet reached us and will not arrive for another 13.5 billion years. Looking around at other galaxies in the JWST deep field image, you can see objects at various distances and therefore various look-back times, creating a view that samples different epochs of cosmic history. The nearest galaxies in the image might be only a few 100 million light-years away, showing us the local universe as it appeared relatively recently. More distant galaxies appear smaller and fainter, showing earlier cosmic epochs. The most distant galaxies are small red smudges, their light heavily redshifted and dimmed by distance and expansion. Together, these galaxies create a time-lapse view of cosmic history, with different objects representing different moments in the universe's evolution. The ability to look back in time by observing distant objects is one of astronomy's unique advantages, and it allows direct observation of how the universe has changed over billions of years. Unlike other sciences that must infer past conditions from present evidence, astronomy can directly observe the past by looking at light that left distant objects long ago. The galaxy you are examining through JWST's data represents a direct observation of the early universe, not a reconstruction or simulation, but an actual image created by photons that left the galaxy 300 million years after the Big Bang. This makes the observation a window into cosmic dawn. The travel time of the light also means there is a fundamental horizon in the observable universe beyond which we cannot see, and this horizon is determined by the age of the universe and the speed of light. Light from objects beyond a certain distance has not had enough time to reach us since the Big Bang, and those objects remain forever invisible, regardless of how powerful our telescopes become. The observable universe is a sphere centered on Earth, with a radius determined by the distance light could have traveled in 13.8 billion years, accounting for cosmic expansion. This radius is about 46 billion light-years, which defines the current particle horizon, or edge of the observable universe. The galaxy you are observing, at 13.5 billion light-years distance, is well within the observable universe, but it is among the most distant galaxies ever detected and lies near the practical limit of what current technology can observe. Galaxies at higher redshifts exist and in principle could be detected, but they become progressively fainter and more difficult to observe as distance increases. JWST is designed to push toward the edge of the observable universe and detect the first galaxies that formed after the Big Bang. And discoveries like this massive early galaxy demonstrate that this ambitious goal is being achieved. Understanding the light's journey through expanding space leads naturally to the question of how we measure that expansion and determine distances to extremely remote objects. The key to distance measurement is redshift, the stretching of light wavelengths caused by cosmic expansion, and measuring redshift allows astronomers to determine both how far away a galaxy is and when in cosmic history it existed. The massive galaxy you have been observing has a measured redshift that places it in the very early universe. And understanding what redshift means and how it is measured reveals why this galaxy's properties are so surprising. The light from the massive early galaxy you are observing has been stretched by cosmic expansion during its journey, and this stretching is called redshift because it shifts light toward longer wavelengths in the direction of the red end of the spectrum. Redshift happens because space itself expands while light is traveling through it, and as space stretches, the wavelengths of light stretch along with it. The amount of stretching tells you how much the universe has expanded since the light was emitted, and this directly relates to how long ago and how far away you are seeing. The redshift of this particular galaxy is estimated to be around Z equals 10 to perhaps Z equals 13 or higher, values that indicate extreme distance and very early cosmic time. Redshift is expressed using the symbol Z, and it is defined mathematically as the change in wavelength divided by the original emitted wavelength. If light is emitted at a wavelength of 100 nanometers and observed at a wavelength of 1000 nanometers, the wavelength has increased by 900 nanometers. Dividing 900 by 100 gives a redshift of Z equals 9, which means the wavelength has been stretched by a factor of 10, or equivalently, that the universe has expanded by a factor of 10 since the light was emitted. For this massive early galaxy, with estimated redshift around Z equals 10, the universe has expanded by a factor of 11 since the galaxy emitted the light you are now observing. The relationship between redshift and cosmic time comes from cosmological models that describe how the universe has expanded over its history. And these models are based on general relativity and observations of the universe's large-scale properties. The standard cosmological model called lambda CDM, includes dark energy, cold dark matter, and ordinary matter, and it describes how the expansion rate has changed over time. Using this model, a redshift of Z equals 10 corresponds to a time when the universe was approximately 500 million years old, about 3.6% of its current age. Higher redshifts correspond to earlier times, with Z equals 20 corresponding to about 200 million years after the Big Bang. Looking at the galaxy's spectrum, if spectroscopic data is available, you would see emission and absorption lines from various elements. And these lines appear at wavelengths shifted from their rest frame laboratory values. Hydrogen produces a series of emission lines called the Lyman series in the ultraviolet part of the spectrum, with the strongest line called Lyman alpha appearing at a rest wavelength of 121.6 nanometers. For a galaxy at redshift Z equals 10, the Lyman alpha line would appear at a wavelength of 120 to 1.6 times 11, which equals 1,337 nanometers, or 1.34 microns in the infrared. JWST's instruments can detect this shifted line and use it to confirm the galaxy's redshift. Oxygen produces emission lines in the ultraviolet and visible parts of the spectrum, and these lines also shift to longer wavelengths for high redshift galaxies. The doubly ionized oxygen line at 507 nanometers, commonly written as 035007, is often bright in star-forming galaxies. At redshift Z equals 10, this line appears at 5,577 nanometers, or 5.58 microns, which is in the mid-infrared range detectable by JWST's mid-infrared instrument. Identifying multiple emission lines in the spectrum allows astronomers to confirm the redshift and ensure that all lines show the same shift, which rules out alternative explanations for the galaxy's colors. The measurement of redshift can be done in two ways, depending on whether you have spectroscopic observations or only images through multiple filters. Spectroscopy provides the most accurate redshift because it directly measures the wavelengths of emission or absorption lines. But spectroscopy requires more telescope time and is typically done for a subset of objects. Photometric redshift estimation uses the galaxy's brightness in multiple filters to estimate the redshift based on how the galaxy's spectrum fits templates of known galaxy types at different redshifts. The massive early galaxy you are observing may have either a spectroscopic redshift or a photometric redshift, depending on which observations have been completed. Photometric redshift works by comparing the observed colors of the galaxy to predicted colors for galaxies at different redshifts, and the redshift that produces the best match is the estimated redshift. A galaxy at high redshift will appear very red, or even invisible in shorter wavelength filters, because the redshift has moved most of the light to longer wavelengths. The galaxy appears progressively brighter in longer wavelength filters as you move into the infrared, where the redshifted light concentrates. The pattern of brightness across filters creates a spectral energy distribution that can be compared to templates, and the best-fitting template gives the photometric redshift estimate. The redshift of this massive galaxy places it at a time when the universe was remarkably different from today. And understanding those differences helps explain why the galaxy's existence is surprising. At redshift Z equals 10, the universe was 11 times smaller in linear dimensions than it is today, which means the volume of space was about 1,300 times smaller. Matter and galaxies were packed much more densely, and the average distance between galaxies was much less than in the modern universe. The higher density meant that galaxies encountered each other and merged more frequently, which influenced how structure grew through cosmic time. The temperature of the cosmic microwave background radiation, which fills all of space as the afterglow of the Big Bang, was 11 times higher at redshift Z equals 10 than it is today. Currently, the CMB has a temperature of 2.7 Kelvin, barely above absolute zero. At Z equals 10, the CMB temperature was about 30 Kelvin, still extremely cold but noticeably warmer. This warmer background radiation affected the thermal state of gas in the early universe and influenced how easily gas could cool and collapse to form stars. The relationship between CMB temperature and redshift is direct. The temperature increases by a factor of 1 plus Z. Looking at the massive early galaxy through the lens of redshift, you can calculate exactly when the light you are seeing was emitted, based on the measured or estimated redshift value. If the redshift is Z equals 10, the light left the galaxy when the universe was 500 million years old. If the redshift is Z equals 13, the light left when the universe was about 350 million years old. The difference matters because it affects how surprising the galaxy's mass is, with higher redshift making the mass more problematic since there was even less time for the galaxy to form. Accurate redshift measurement is crucial for understanding whether this galaxy truly challenges our models, or whether it is less extreme than initial estimates suggested. The expansion of the universe that causes redshift is an expansion of space itself, and it is important to understand that galaxies are not moving through space away from us, but rather that space between us and distant galaxies is growing. This distinction matters for understanding cosmology and the nature of cosmic expansion. If galaxies were moving through space, their motion would be limited by the speed of light, and we could not see objects receding faster than light speed. But because space itself expands, distant objects can have recession velocities greater than the speed of light, without violating relativity, and the redshift can in principle be arbitrarily large. The recession velocity for this massive early galaxy can be calculated from its redshift, using the relationship between redshift and velocity for nearby objects. But at these high redshifts, the simple relationship breaks down, and you need the full cosmological equations. For small redshifts, the recession velocity is approximately the speed of light times the redshift, so Z equals 0.1 corresponds to 10% of light speed. But for Z equals 10, the relationship is more complex, and the actual recession velocity of the galaxy at the time the light was emitted was several times the speed of light. This does not mean the galaxy was moving faster than light through space, but rather that space was expanding so rapidly that the distance between us and the galaxy was increasing at that rate. The concept of looking back in time through redshift means that every observation of a distant galaxy is an observation of the early universe, and deeper observations reveal progressively earlier cosmic epochs. JWST is designed to observe the highest redshift galaxies possible, targeting redshifts from Z equals 10 to Z equals 20, or potentially higher. These redshifts correspond to the epoch of cosmic dawn, when the first stars and galaxies formed, and when the universe transformed from a dark neutral state to an ionized state, filled with starlight. Observing galaxies in this redshift range fulfills one of JWST's primary science goals. The massive galaxy you are observing falls right into this crucial redshift range, and its properties provide information about how galaxy formation proceeded during cosmic dawn. The redshift tells you when you are seeing, and the galaxy's brightness and structure tell you what exists at that time. Combining these pieces of information reveals the apparent contradiction. At the time indicated by the redshift, galaxies were expected to be small and less massive based on theoretical models developed before JWST began observing. The fact that this galaxy appears massive and structurally mature at such high redshift is what makes the discovery surprising and scientifically interesting. Understanding redshift and what it reveals about cosmic time sets the stage for understanding the surprise that these massive early galaxies represent. Before JWST, astronomers had developed detailed models of galaxy formation based on our understanding of physics, dark matter, and the initial conditions set by the Big Bang. These models made specific predictions about what galaxies should look like at different redshifts, including predictions for the maximum mass that galaxies could achieve by any given cosmic time. When JWST observed the early universe and found massive galaxies at very high redshifts, those observations appeared to contradict the predictions, and understanding why requires examining what the models predicted before JWST revealed the actual early universe. Before the James Webb Space Telescope began its observations, astronomers had spent decades building theoretical models of how galaxies form and evolve over cosmic time, and these models made specific predictions about what the early universe should look like. The models started from the conditions established by the Big Bang and the cosmic microwave background, which showed that the early universe was extremely uniform with only tiny density fluctuations. These tiny fluctuations were the seeds of all structure that would later form, and computer simulations traced how gravity amplified these seeds into the galaxies and galaxy clusters we see today. The simulations predicted a gradual hierarchical growth, where small objects formed first and merged over billions of years to create larger galaxies. The physics incorporated into these models included the behavior of dark matter, which does not interact with light but exerts gravitational influence and provides the scaffolding for galaxy formation. Dark matter began collapsing into concentrated clumps called halos shortly after the Big Bang, and these halos grew over time through mergers and by accreting more dark matter from their surroundings. Normal matter, which consists of protons, neutrons, and electrons that make up the gas and stars we can see, fell into the gravitational wells created by dark matter halos. Once normal matter concentrated in these wells, it could cool and eventually collapse to form stars, creating the first galaxies. The timeline predicted by these models suggested that the first stars formed somewhere between 100 and 200 million years after the Big Bang, and these stars were very different from stars forming today. Called population 3 stars, they formed from primordial gas containing only hydrogen and helium, with essentially no heavier elements, and theoretical models suggested they were very massive and short-lived. These first stars produced the first heavy elements through nuclear fusion and released them into space when they died, enriching the gas from which later generations of stars would form. The first small galaxies assembled from collections of these early stars and their successors. According to the pre-JWST models, early galaxies at redshifts around Z=10 should have masses ranging from a few million to perhaps 10 billion solar masses, with the most massive early galaxies being rare. The models predicted that building up a mass of 100 billion solar masses, comparable to the Milky Way's stellar mass, would require several billion years of star formation and galaxy mergers. At Z=10, corresponding to 500 million years after the Big Bang, the models indicated that galaxies should still be in the process of assembling, and that truly massive galaxies had not yet formed. The expected maximum mass at Z=10 was around 10 to 20 billion solar masses at most, and even reaching this mass required exceptionally favorable conditions. Looking at the predictions for galaxy properties beyond just mass, the models suggested that early galaxies should appear irregular and clumpy, rather than showing the organized spiral or elliptical structures seen in mature galaxies. The development of smooth disks and spiral arms requires time for the gas and stars to settle into organized rotation under gravity, and this process takes hundreds of millions to billions of years. At Z=10, the models predicted that most galaxies would show chaotic morphologies with multiple bright star-forming knots rather than coherent structure. The simulated images of early galaxies from these models showed small, irregular blobs rather than the well-defined forms characteristic of later galaxies. The star formation rates predicted for early galaxies were expected to be high compared to their masses, with young galaxies forming new stars rapidly from their abundant gas supplies. However, the absolute rate of star formation was limited by how quickly gas could cool and collapse, and by feedback processes that remove gas or heat it to temperatures where it cannot form stars. Supernovae from massive stars explode and inject energy into the surrounding gas, heating it and potentially driving it out of the galaxy entirely. Stellar winds from massive stars also carry away material and energy. These feedback mechanisms regulate star formation and prevent all the gas from turning into stars immediately. The models incorporated these feedback processes and predicted that early galaxies would form stars at rates ranging from a few solar masses per year up to perhaps 100 solar masses per year in the most extreme cases. Even at 100 solar masses per year, accumulating 100 billion solar masses would take 1 billion years, which is twice as long as the age of the universe at Z=10. This arithmetic set a firm upper limit on galaxy masses at early times, according to the models, and it is part of why finding massive galaxies at very high redshifts has been surprising. The dark matter halo masses, predicted at early times, also imposed constraints on galaxy masses through the relationship between halo mass and the stellar mass of the galaxy forming within the halo. Not all the matter in a dark matter halo turns into stars, and in fact, the efficiency of converting baryonic matter into stars is relatively low, typically around 10 to 20%. The most massive dark matter halos predicted to exist at Z equals 10 had masses around 1 trillion solar masses, which would host galaxies with stellar masses around 10 to 20 billion solar masses, using the typical efficiency. Halos massive enough to host 100 billion solar mass galaxies were predicted to be extraordinarily rare or non-existent at such early times. Computer simulations, like the Illustris simulation, the Eagle simulation, and others, ran detailed models of galaxy formation across cosmic time, and these simulations generally agreed on the timeline of structure growth. The simulations began with initial conditions matched to the cosmic microwave background observations and evolved forward in time using the equations of gravity, hydrodynamics, star formation, and feedback. The results showed gradual growth, with small galaxies forming first and merging to create progressively larger systems. By Z equals 10 in these simulations, the largest galaxies had masses around 5 to 10 billion solar masses, consistent with the analytical estimates. Observations with the Hubble Space Telescope before JWST launched provided data on galaxies at redshifts up to about Z equals 8 or 9, and these observations generally matched the model predictions. Hubble found galaxies at Z equals 7 to 8, with masses ranging from a few hundred million to a few billion solar masses, which aligned well with theoretical expectations. The galaxies appeared small and often irregular, consistent with predictions for young forming systems. These observations gave astronomers confidence that the models were on the right track and provided a reasonable description of early galaxy formation. Extrapolating from the Hubble observations to higher redshifts, astronomers expected that JWST would find even smaller and younger galaxies as it pushed to Z equals 10 and beyond. The predictions suggested that at Z equals 10 to 15, galaxies would be primarily low-mass systems, still in the process of forming their first major generations of stars. Massive galaxies were expected to be absent or extremely rare at these redshifts, and any objects with masses approaching 100 billion solar masses were thought to appear only at lower redshifts, corresponding to later cosmic times, when there had been sufficient time for growth. The theoretical framework underlying these predictions was based on the Lambda CDM cosmological model, which has been extraordinarily successful at explaining observations ranging from the cosmic microwave background to the large-scale distribution of galaxies. Lambda CDM specifies the amounts of dark energy, dark matter, and normal matter in the universe, and it describes how the universe has expanded over time. The model's predictions for the growth of structure match observations of the cosmic web and galaxy clustering, giving high confidence in its basic correctness. The galaxy formation models built within this framework were considered reliable for predicting the statistical properties of galaxy populations at different cosmic epochs. Given this theoretical foundation, and the supporting observations from Hubble, the expectation was that JWST would see the early universe populated by small young galaxies, gradually building up mass, confirming and refining the detailed predictions of the models. The discovery of massive, apparently mature galaxies at very high redshifts was not part of the expected picture. And when the first JWST deep field images revealed bright, massive early galaxies, the scientific community responded with a mixture of excitement and puzzlement. The observations appeared to show that nature had found a way to build massive galaxies much faster than the models predicted, which either meant the models were missing important physics or that the observations required careful re-examination. The predictions established before JWST created a baseline against which the actual observations could be compared. And the discrepancy between prediction and observation is what defines the surprise of finding massive early galaxies. Understanding what was predicted helps clarify why the discoveries matter and what questions they raise about galaxy formation physics. The models were not wild guesses, but sophisticated simulations based on well-tested physics and observational constraints, which makes the discrepancy between model predictions and JWST observations scientifically significant and worthy of detailed investigation. The stage is set for understanding the surprise. Models predicted small young galaxies at very high redshifts, with maximum masses around 10 billion solar masses at Z equals 10, and lower masses at higher redshifts. When JWST began observing the early universe, it found something different. Galaxies that appeared far more massive than the predictions allowed. And this discovery prompted immediate scientific attention and debate about what these objects really are and what they reveal about the early universe. When the first deep field images from the James Webb Space Telescope were released in July 2022, astronomers examining the data began noticing galaxies that appeared unexpectedly bright and massive at very high redshifts. The initial observations came from surveys like TEARS, which stands for Cosmic Evolution Early Release Science, and GLASS, the Grism Lens Amplified Survey from space, along with other programs targeting the early universe. These surveys captured thousands of galaxies in single images, and among them were candidates that showed photometric colors consistent with extreme distances, but also showed brightness levels that suggested large stellar masses. The combination of high redshift and high mass was immediately recognized as surprising. Looking at the brightness measurements from these galaxies, you can see that they shine intensely in the infrared wavelengths, where JWST observes, and brightness in galaxies typically correlates with stellar mass because more stars produce more light. The relationship between brightness and mass depends on the ages and types of stars in the galaxy, with young hot stars producing much more light per unit mass than old cool stars. But even accounting for the brightest possible stellar populations, the observed brightness of these early galaxies suggested stellar masses in the range of tens of billions to over 100 billion solar masses. These values were roughly 10 times higher than the maximum masses predicted by models for galaxies at redshifts around Z equals 10 to 13. The initial mass estimates came from analyzing the spectral energy distribution, which is the pattern of brightness across multiple wavelength filters, and fitting models to this pattern to determine the galaxy's properties. The models used in this fitting process account for stellar populations of different ages, metallicities, and formation histories, and they predict how bright a galaxy should appear in each filter based on these properties. The best-fitting models for several early JWST candidates indicated stellar masses exceeding 100 billion solar masses, with some estimates reaching several hundred billion solar masses. These masses are comparable to or greater than the Milky Way's stellar mass, which has accumulated over 13 billion years. The structural properties visible in the JWST images added to the surprise because the galaxies did not appear as the small irregular clumps predicted by models, but rather showed organized morphologies. Some candidates displayed disk structures with clear central concentrations and extended outer regions, while others showed compact but symmetric forms. The presence of structure suggested that these galaxies had already undergone significant evolution and settling processes that were thought to require substantial time. Finding structured galaxies at times when the universe was only 300 to 500 million years old contradicted the expectation that galaxies would still be in chaotic assembly phases. One particular galaxy candidate that drew attention was designated EIS 93316, which appeared in the CERS survey field and initially showed photometric colors consistent with a redshift around Z equals 16. If this redshift was correct, the galaxy existed only about 250 million years after the Big Bang, and the estimated stellar mass was around 100 billion solar masses. The combination seemed almost impossible according to standard galaxy formation theory, because forming such a massive galaxy in such a short time would require star formation rates averaging several hundred million solar masses per year continuously from the Big Bang to the time of observation. Looking at the numbers more carefully reveals the magnitude of the challenge these galaxies pose to theoretical models. If you have 250 million years and need to form 100 billion solar masses of stars, the average star formation rate must be 100 billion divided by 250 million, which equals 400 solar masses per year. This average must be sustained continuously throughout the entire available time period, with no interruptions or slow periods. For comparison, the Milky Way currently forms about 2 solar masses per year, and the most extreme starburst galaxies observed in the local universe reach star formation rates around 1,000 solar masses per year for brief periods. Requiring 400 solar masses per year sustained for hundreds of millions of years seems implausible. The challenge becomes even more severe when you consider that star formation cannot begin immediately after the Big Bang, and some time must elapse for the first dark matter halos to collapse, and for gas to accumulate and cool sufficiently to form stars. The first stars likely formed around 100 to 200 million years after the Big Bang, which means the actual time available for building up the mass is even shorter than the total age of the universe at observation. If star formation began at 150 million years, and the galaxy is observed at 250 million years, only 100 million years are available, which raises the required average star formation rate to 1 billion solar masses per year. This exceeds observed starburst rates by factors of hundreds or thousands. The initial reports of these massive, high redshift candidates generated considerable excitement in the astronomical community, and several research groups published papers analyzing the JWST data and discussing the implications. Terms like universe breakers appeared in some discussions, suggesting that these galaxies might break or contradict the standard cosmological model. The phrase was somewhat sensational and not fully accurate, as the observations challenged specific galaxy formation models rather than the underlying cosmology. But the term captured the sense that something unexpected had been found, and that existing theoretical frameworks might need revision. Multiple massive galaxy candidates emerged from different JWST surveys, indicating that the phenomenon was not limited to a single object, but represented a potentially common population. The GLASS survey identified candidates. The JDAC's survey found candidates at redshifts around Z equals 13 to 14, and other programs contributed additional discoveries. The number of massive early galaxy candidates grew to dozens within the first year of JWST operations, and the pattern suggested that massive galaxies at high redshift were more abundant than pre-JWST models had predicted. The abundance was as surprising as the individual masses, because models predicted that massive early galaxies should be extremely rare. Looking at the distribution of these candidates across the sky, you find them scattered through the deep fields that JWST has observed, and they do not concentrate in any particular region. The candidates appear wherever JWST looks deeply enough to detect high redshift galaxies, which suggests they represent a general population rather than a fluke or local overdensity. Some candidates appear in regions that also show other high redshift galaxies nearby, indicating clustering and suggesting that structure formation was already creating galaxy groups and protoclusters in the early universe. The environmental context of these massive early galaxies provides additional information about how they formed. The spectral energy distributions of the candidates show the characteristic shape expected for high redshift galaxies, with strong suppression at short wavelengths where the Lyman break occurs and bright emission in longer wavelength filters. The Lyman break is a feature caused by absorption of light at wavelengths shorter than the Lyman limit at 91.2 nanometers by neutral hydrogen. And for high redshift galaxies, this break shifts into the near infrared where JWST observes. The position of the break in the observed wavelengths indicates the redshift, and the brightness at wavelengths longer than the break indicates the stellar mass. The combination allows photometric redshift estimation and mass estimation from the same set of filter images. Some candidates showed additional features in their spectral energy distributions that suggested the presence of very old stellar populations, which would be surprising at such early cosmic times. Old stars produce less light per unit mass than young stars and create characteristic features in galaxy spectra, including a prominent break at 4,000 angstroms called the Balmer break. For high redshift galaxies, this break shifts into the infrared, and detecting it suggests that the galaxy contains stars that are already several 100 million years old. Finding old stars in galaxies observed only 300 to 500 million years after the Big Bang, implies that star formation must have begun very early, potentially only tens of millions of years after the Big Bang. The initial mass estimates for these JWST candidates carried significant uncertainties, and astronomers recognized that multiple factors could affect the derived values. The photometric redshifts could be uncertain, particularly for galaxies without spectroscopic confirmation, and some candidates might be at lower redshifts than their photometric estimates suggested. The stellar mass estimates depend on assumptions about the stellar initial mass function, which describes the distribution of masses for newly formed stars, and a different IMF would produce different mass estimates from the same observed brightness. Dust extinction could also affect the observations, with dust absorbing some light and altering the galaxy's colors. Despite these uncertainties, the pattern of finding numerous apparently massive galaxies at high redshift was robust enough to indicate that something interesting was happening in the early universe. Even if some individual candidates were later found to be at lower redshift or to have lower masses than initially estimated, the overall population suggested that galaxy formation in the early universe proceeded more efficiently than pre-JWST models predicted. The surprise was real and scientifically significant, indicating that our understanding of early galaxy formation needed refinement or revision to account for the observations. The brightness of these galaxies in JWST images shows that they are substantial objects producing significant amounts of light, and regardless of the exact stellar masses, they represent important star-forming systems in the early universe. The light you see from them indicates active stellar populations and ongoing or recent star formation, and the structure, visible in some cases, indicates that gravitational processes have organized the material into coherent configurations. These are not tentative first galaxies, barely emerging from the cosmic dark ages, but rather robust systems that have already achieved considerable development. Looking at one of these massive galaxy candidates in a JWST image, you see an object that appears similar to lower redshift galaxies in terms of structure and brightness, and only the redshift information reveals that you are seeing something from cosmic dawn. The visual similarity between these early massive galaxies and later galaxies suggests that the processes forming galaxies operated efficiently even in the early universe, and that the appearance of mature galaxies happened sooner than expected. This visual similarity is part of what makes the discoveries surprising. The realization that the early universe was already producing galaxies that look recognizably like the galaxies we see at later times. The surprise of finding massive early galaxies has prompted astronomers to ask how such objects could form so quickly. And answering this question requires examining the methods used to estimate galaxy masses and considering whether the mass estimates are accurate. Understanding how stellar mass is determined from observations is crucial for evaluating whether these galaxies truly are as massive as they appear, or whether some aspect of the analysis might be overestimating their masses. The next step in understanding these objects involves exploring the measurement techniques and the potential uncertainties that could affect the derived masses. Determining the mass of a galaxy from telescope observations requires inferring the total amount of stellar material from the light that the galaxy emits. And this inference depends on understanding the relationship between stellar mass and luminosity. Stars produce light through nuclear fusion in their cores, and the luminosity of a star depends on its mass, with more massive stars shining much brighter than less massive stars. A star 10 times the mass of the Sun produces roughly 10,000 times as much light, while a star half the mass of the Sun produces only about 3% as much light as the Sun. This steep mass-luminosity relationship means that a few massive stars can outshine many low-mass stars. The total light from a galaxy comes from all its stars combined, and determining the stellar mass requires knowing how many stars of each mass are present. Astronomers use stellar population models that simulate the light output from collections of stars with specified age distributions, metallicities, and initial mass functions. The initial mass function, often abbreviated IMF, describes what fraction of stars form at each mass. And observations of nearby star-forming regions suggest that most stars form at low masses, with progressively fewer stars forming at higher masses. The Salpeter IMF and the Chabrier IMF are commonly used forms that encode this distribution. Applying stellar population models to observations involves measuring the galaxy's brightness in multiple wavelength filters and comparing the observed spectral energy distribution to predicted distributions. From models, the models predict how bright a galaxy should appear in each filter based on the stellar population parameters, and varying those parameters produces different predicted brightnesses. The parameter combination that best matches the observed brightnesses is adopted as the best estimate for the galaxy's properties. This process is called SED fitting, which stands for spectral energy distribution fitting, and it is the primary method for estimating stellar masses from photometric observations. Looking at the JWST observations of massive early galaxies, the SED fitting process uses the galaxy's brightness in JWST's multiple near-infrared filters, along with any available data from other wavelengths. JWST's NIRCam instrument has filters ranging from about 0.9 microns to 5 microns, and this coverage spans the wavelength range where high redshift galaxies emit most of their redshifted light. The brightness pattern across these filters reveals the shape of the galaxy's spectrum, and this shape depends on the stellar population properties. A galaxy with primarily young hot stars shows a relatively flat or blue spectrum, while a galaxy with older cooler stars shows a redder spectrum with more light at longer wavelengths. The mass-to-light ratio is a key concept in converting observed luminosity to stellar mass, and this ratio describes how much mass exists per unit of light output. Young stellar populations have low mass-to-light ratios because they contain many massive bright stars, so a given amount of light corresponds to relatively little stellar mass. Old stellar populations have high mass-to-light ratios because the massive bright stars have already died, leaving only the long-lived low-mass stars that produce little light per unit mass. The mass-to-light ratio can vary by factors of 10 or more, depending on stellar population age. For the massive early galaxies observed by JWST, the SED fitting must determine whether the observed brightness comes from a small mass of young bright stars or a large mass of older dimmer stars. The colors of the galaxy help distinguish these cases because young stars produce more ultraviolet and blue light, while older stars produce more red and infrared light. A galaxy that appears very bright in the shortest wavelength, JWST filters, likely contains young stars, while a galaxy that appears relatively brighter in longer wavelength filters may contain older stellar populations. The detailed shape of the brightness across filters allows models to estimate the age and mass-to-light ratio. Dust complicates the mass estimation process because dust grains in galaxies absorb and scatter light, particularly at shorter wavelengths. And this absorption can make a galaxy appear redder than it would without dust. Dust extinction preferentially removes blue and ultraviolet light, while allowing red and infrared light to pass through more easily, creating an effect that mimics the presence of old red stars. Distinguishing between dust reddening and intrinsic stellar population redness requires careful modeling, and uncertainties in the dust content contribute to uncertainties in the derived stellar masses. JWST's infrared observations help because infrared light penetrates dust better than visible light, but dust still affects the measurements. The choice of stellar initial mass function affects the mass estimate significantly, because different IMFs predict different numbers of stars at each mass for a given total stellar mass. A bottom-heavy IMF with many low-mass stars and few high-mass stars produces less light per unit mass than a top-heavy IMF with more high-mass stars. If the actual IMF in early galaxies differs from the IMF assumed in the models, the derived masses could be systematically wrong. Some researchers have suggested that early galaxies might have top-heavy IMFs due to different gas conditions in the metal-poor early universe. And if this is true, the bright early galaxies could have less mass than standard IMF assumptions suggest. Looking at the uncertainties in stellar mass estimates for individual galaxies, astronomers typically quote uncertainties of factors of 2 to 3, meaning that a galaxy estimated to have 100 billion solar masses might actually have anywhere from 30 billion to 300 billion solar masses. These uncertainties come from degeneracies in the SED fitting, where different parameter combinations can produce similar observed colors, making it difficult to uniquely determine all parameters. The degeneracies are particularly strong when only photometric data is available without spectroscopy, because spectroscopy breaks some degeneracies by providing precise measurements of emission line strengths and positions. Spectroscopic observations provide more accurate stellar mass estimates because spectra reveal detailed information about the stellar populations and gas properties, and emission line ratios can indicate star formation rate, metallicity, and ionization state. JWST's NIR spec instrument can obtain spectra of high redshift galaxies, and several of the massive early galaxy candidates have been observed spectroscopically to confirm their redshifts and study their properties. The spectroscopic observations generally confirm the high redshifts estimated photometrically for most objects, though some candidates have been found to be lower redshift interlopers with properties that mimic high redshift galaxies. The phenomenon of lower redshift interlopers can occur because certain types of galaxies at moderate redshifts can have colors similar to genuine high redshift galaxies. Dusty star-forming galaxies at redshifts around Z=2 to 4 can appear very red due to dust extinction, and their faintness at short wavelengths combined with brightness at long wavelengths can mimic the Lyman break expected for high redshift galaxies. Distinguishing these interlopers requires spectroscopy or very careful photometric analysis with many filters. Some of the initial massive galaxy candidates from early JWST observations have been identified as lower redshift objects upon follow-up spectroscopy, which reduces the number of confirmed massive early galaxies, but does not eliminate the population entirely. Even accounting for interlopers and measurement uncertainties, a core population of genuinely high redshift, massive galaxies remains confirmed by spectroscopy at redshifts around Z=10 to 14. These confirmed objects include galaxies like JWST Z13-0, which has a spectroscopic redshift of Z=13.2, and several other candidates with secure spectroscopic conformations. The confirmed galaxies show stellar mass estimates ranging from tens of billions to over 100 billion solar masses, depending on the modeling assumptions, and these masses remain challenging for theoretical models, even at the lower end of the uncertainty range. The mass measurements also depend on the cosmological model used to convert redshift to distance and look-back time, though the lambda CDM model is so well constrained by other observations that cosmological uncertainties are small compared to astrophysical uncertainties. The stellar mass depends on the assumed distance, because luminosity is calculated from observed brightness and distance, and the distance comes from the redshift and the cosmological model. Changes to cosmological parameters within their allowed ranges would shift stellar mass estimates by perhaps 10 to 20%, which is small compared to the factor of 2 to 3 uncertainties from astrophysical parameters like IMF and dust. Looking at the overall picture of mass measurements for early JWST galaxies, the evidence suggests that a population of massive galaxies exists at redshifts around Z=10 to 14, with stellar masses likely in the range of tens of billions of solar masses, and possibly exceeding 100 billion solar masses in some cases. The exact masses remain uncertain and continue to be refined as more spectroscopic data becomes available and as modeling techniques improve. But the existence of this population is robust to reasonable uncertainties, and explaining how these galaxies formed so quickly remains a challenge for galaxy formation theory. The challenge comes into sharp focus when you consider the time available for forming these masses, and this timeline problem is what makes the massive early galaxies surprising and scientifically significant. Understanding the timeline constraints requires examining how long it takes to form stars and assemble galaxies, and comparing that to the age of the universe when these objects are observed. The apparent mismatch between required formation time and available time is the core of the puzzle that astronomers are working to resolve. The fundamental timeline problem with the massive early galaxies becomes clear when you calculate how quickly stars must form to build up the observed stellar masses in the time available. If a galaxy at redshift Z=10 has a stellar mass of 100 billion solar masses, and the universe was 500 million years old when the light left the galaxy. Then, 100 billion solar masses of stars must have formed within, at most, 500 million years. In reality, the time available is even shorter, because star formation cannot begin immediately after the Big Bang, and some time must pass for structure to collapse and conditions to become suitable for forming the first stars. The first stars likely formed around 100 to 200 million years after the Big Bang, based on theoretical models and emerging observational constraints. And this means the actual time available for forming a massive galaxy, observed at 500 million years, is only about 300 to 400 million years. Dividing 100 billion solar masses by 300 million years gives an average star formation rate of 333 million solar masses per year. And this average must be sustained continuously throughout the entire period. This required rate is extraordinarily high compared to observed star formation rates in both nearby galaxies and other high redshift galaxies that have been studied. Looking at star formation rates in the modern universe for comparison, the Milky Way currently forms about 1 to 2 solar masses of new stars per year, and this rate is typical for large spiral galaxies in the present epoch. Star formation was more vigorous in the past, when galaxies had more available gas, and observations of galaxies at redshifts around Z equals 1 to 2 show star formation rates of tens to hundreds of solar masses per year in normal star-forming galaxies. The most extreme starburst galaxies, which are undergoing intense episodes of star formation, triggered by galaxy mergers or other events, can reach star formation rates around 1,000 solar masses per year for brief periods, typically lasting tens to hundreds of millions of years. Sustaining star formation rates of hundreds of millions of solar masses per year for hundreds of millions of years seems implausible based on our understanding of the physical processes that regulate star formation. Gas must cool and collapse to reach the high densities required for star formation, and cooling takes time, even under favorable conditions. Once stars form, they inject energy back into the surrounding gas through stellar winds, radiation pressure, and supernova explosions. And this feedback heats the gas and can drive it out of the galaxy entirely. Feedback processes are thought to be the primary mechanism that prevents all the gas in galaxies from turning into stars immediately, and they set upper limits on sustainable star formation rates. The available gas supply also constrains how fast stars can form. And even if feedback was somehow suppressed, star formation cannot proceed faster than gas can fall into the galaxy. Dark matter halos grow through accretion and mergers, and baryonic matter falls into these halos at rates determined by the cosmological growth of structure. For a dark matter halo at redshift Z equals 10, the gas infall rate depends on the halo mass, and typical estimates suggest infall rates of tens to perhaps 100 solar masses per year for the most massive halos expected at that time. Even if all the infalling gas immediately turned into stars without any feedback, the star formation rate would be limited to the infall rate. Considering that star formation efficiency, defined as the fraction of infalling gas that actually forms stars, is typically around 10 to 20% based on observations and models, The expected star formation rates at Z equals 10 are much lower than the hundreds of millions of solar masses per year required to explain the massive early galaxies. The efficiency is low because feedback processes remove most of the gas before it can form stars, and because much of the gas remains in diffuse hot phases that do not cool and collapse. Achieving the required star formation rates would demand efficiencies approaching 100%, meaning all infalling gas immediately turns into stars, with no feedback and no losses, which contradicts everything we understand about star formation physics. The timeline problem becomes even more severe when you consider that the stellar mass observed in a galaxy represents only the stars that still exist at the time of observation, and additional mass was locked up in stars that already died by that time. Massive stars live only a few million years before exploding as supernovae, and if a galaxy has been forming stars for hundreds of millions of years, multiple generations of massive stars have formed and died. The mass in these dead stars and their remnants must be added to the currently visible stellar mass to get the total mass that must have been formed. This can increase the required total star formation by perhaps 20 to 50%, depending on the stellar populations involved. Looking at the problem from another angle, you can ask, what fraction of the available baryonic matter must turn into stars to achieve the observed stellar masses? The cosmic baryon fraction is about 16%, meaning that for every unit of dark matter, there are 0.16 units of baryonic matter consisting of normal atoms. If a galaxy forms in a dark matter halo of 1 trillion solar masses, the total baryonic mass available is 160 billion solar masses. If 100 billion solar masses are in stars, that represents a conversion efficiency of 60% of available baryons into stars, which is much higher than the typical 10 to 20% seen in galaxies across cosmic time. The required high efficiency raises questions about what prevents the gas from being lost to feedback or remaining in non-star forming phases. And standard models predict that feedback should be even stronger in the early universe due to the lower metallicity of the gas. Metal-poor gas cannot cool as efficiently through metal line radiation, which might make it harder to form stars rather than easier. The lower cooling efficiency would tend to keep gas hot and prevent it from collapsing into dense, star-forming clouds. This is opposite to what would be needed to explain the rapid formation of massive early galaxies, which requires gas to cool efficiently and form stars at unprecedented rates. The dark matter halo masses themselves are constrained by cosmology and the growth of structure from the initial density fluctuations measured in the cosmic microwave background, and the statistical distribution of halo masses at any given time is predicted by the lambda CDM model with relatively small uncertainties. At redshift Z equals 10, halos massive enough to host galaxies with 100 billion solar masses in stars are predicted to be extremely rare, with perhaps only a handful existing in the entire observable universe. Yet, JWST finds multiple such galaxies in the relatively small volumes surveyed by deep field observations, suggesting either that the halo mass function is different from predicted, or that galaxies formed more efficiently in lower mass halos than models expected. The timescale for galaxy assembly through mergers also creates constraints, and mergers take time to complete as galaxies orbit each other and eventually coalesce. If the massive early galaxies formed primarily through mergers of smaller galaxies, the number of mergers required and the time for each merger must fit within the available cosmic time. Simulations of galaxy mergers suggest that major mergers between similar mass galaxies take several 100 million years from initial encounter to final coalescence. And building a massive galaxy through multiple sequential mergers would require even more time. The time constraints make it difficult for hierarchical assembly through mergers to produce the most massive early galaxies observed by JWST. Looking at all these timeline constraints together, the conclusion is that forming galaxies with stellar masses around 100 billion solar masses by redshift Z equals 10 requires either much higher star formation efficiencies than standard models predict, or much earlier start times for star formation, or both. Alternative explanations might involve different stellar populations that produce more light per unit mass, which would reduce the inferred masses, or contributions from active galactic nuclei that add non-stellar light and make the galaxies appear more massive than they actually are. Each of these possibilities is being investigated by astronomers working to understand the JWST observations. The timeline problem is real and significant, and it represents a genuine challenge to pre-JWST galaxy formation models. The models were not arbitrary, but based on well-understood physics and observational constraints from studies of lower redshift galaxies and cosmic structure. Finding that nature can form massive galaxies faster than these models predicted indicates that some aspect of the models needs revision. The revision might involve changes to assumed parameters, like star formation efficiency or feedback strength, or it might require incorporating new physical processes that were not included in previous models. Understanding which revisions are needed requires examining possible explanations for how massive galaxies could form so quickly. Several possible explanations have been proposed to resolve the apparent contradiction between the observed massive early galaxies and the predictions of galaxy formation models, and each explanation involves different assumptions about either the observations or the physics of galaxy formation. The explanations fall into a few broad categories, including measurement uncertainties that might reduce the problem, astrophysical processes that could enable faster galaxy growth, and alternative interpretations of what the observations are showing. Astronomers are actively investigating these possibilities, using additional JWST observations and refined theoretical modeling to determine which explanations are most likely correct. The first category of explanations involves questioning whether the observed galaxies are actually as massive and as distant as initial estimates suggest, and several factors could lead to overestimates of mass or redshift. Photometric redshift estimates can be uncertain, particularly for individual objects, and some galaxies initially identified as high redshift candidates could actually be at lower redshifts, where their masses would be less problematic. Lower redshift dusty galaxies can mimic the colors of high redshift galaxies, appearing very red due to dust extinction that suppresses their shorter wavelength light. Spectroscopic follow-up is needed to confirm redshifts, and some candidates have indeed turned out to be lower redshift interlopers. For galaxies with confirmed spectroscopic redshifts at Z greater than 10, the distance and look-back time are secure. But the stellar mass estimates still carry uncertainties related to stellar population modeling. The stellar initial mass function is a key uncertainty because different assumptions about the IMF change the mass-to-light ratio significantly. If early galaxies had top-heavy IMFs with more high-mass stars than assumed in standard models, they would produce more light per unit stellar mass, and the inferred masses from observed brightness would be lower. A top-heavy IMF could arise in metal-poor environments where the gas properties differ from conditions in the modern universe, and some theoretical work suggests this is plausible. Looking at dust as another source of uncertainty, heavy dust obscuration could affect the observed colors and brightness in ways that complicate mass estimates. If early galaxies contained more dust than models assume, that dust could absorb light and alter the spectral energy distribution, potentially leading to incorrect stellar population ages or masses. However, producing large amounts of dust requires previous generations of stars to create the heavy elements from which dust grains form. And in the very early universe, the metallicity should be low, with correspondingly low dust content. Whether early massive galaxies could have significant dust remains an open question, requiring more detailed observations. The second category of explanations involves astrophysical processes that could enable faster galaxy growth than standard models predict. And these include higher star formation efficiencies, weaker feedback, and more efficient gas accretion. Star formation efficiency could be higher in the early universe if gas cooling was more efficient than models assume, perhaps due to molecular hydrogen cooling in primordial gas, or due to different turbulent conditions in early dark matter halos. If a larger fraction of the gas in halos could cool and collapse to form stars, galaxies would build up mass more quickly without requiring higher gas infall rates. Feedback processes could be weaker in the early universe than in later epochs, allowing more gas to remain in galaxies and form stars rather than being ejected. Supernova feedback depends on the coupling of explosion energy to the surrounding gas, and in denser environments, that coupling might be less efficient, allowing the gas to retain more of its mass despite ongoing star formation. Stellar wind feedback might also be weaker if stellar metallicity is lower, since metals in stellar atmospheres contribute to driving winds through radiation pressure. Weaker feedback would permit higher star formation efficiencies and faster mass buildup. Dark matter halos could have grown faster in the early universe if the density fluctuations that seeded structure formation were larger on small scales than currently assumed, and this would provide more massive halos earlier and enable faster galaxy assembly. The density fluctuation power spectrum is measured by the cosmic microwave background on large scales, but small-scale fluctuations are less well constrained, and it is possible that structure formation on galaxy scales proceeded faster than extrapolations from large scales would suggest. More massive early halos would provide deeper gravitational potential wells and higher gas infall rates, enabling more rapid star formation. Looking at alternative formation pathways, some researchers have suggested that early galaxies might have formed through direct collapse of gas into massive objects, rather than through the standard bottom-up hierarchical assembly. Direct collapse scenarios could produce massive galaxies more quickly by skipping the stage of forming many small galaxies that later merge. For direct collapse to occur, conditions must be right for large gas clouds to collapse while avoiding fragmentation into many small objects. And this might require special conditions in the early universe, such as strong radiation backgrounds that suppress cooling and fragmentation. Direct collapse is most often discussed in the context of forming supermassive black holes, but related ideas might apply to rapid galaxy formation. The third category of explanations involves alternative interpretations of what the bright early galaxies represent, and these include contributions from active galactic nuclei that could mimic stellar light. Active galactic nuclei, abbreviated AGN, are powered by supermassive black holes accreting matter at the centers of galaxies, and they can shine as brightly as entire galaxies, despite the light coming from a very small region near the black hole. If early massive galaxy candidates contain AGN that contribute significantly to their observed light, the stellar masses inferred from brightness would be overestimates, because some light comes from the AGN rather than stars. Distinguishing AGN from stellar light requires spectroscopy that can identify characteristic emission lines and line ratios indicative of AGN, and JWST spectroscopic observations of some early massive galaxies have revealed signatures of AGN in several cases. The presence of AGN does not necessarily mean the galaxies are less massive, since AGN and massive stellar populations can coexist. But it does complicate the mass estimates and requires careful separation of stellar and AGN contributions to the light. Some of the brightest early galaxy candidates may be AGN-dominated objects where most of the observed light comes from the black hole rather than stars, which would resolve their apparently impossible masses. The formation of supermassive black holes in the early universe is itself a puzzle related to the massive galaxy problem, and observations of high redshift quasars show that billion solar mass black holes existed when the universe was less than 1 billion years old. Forming such massive black holes quickly requires either very high accretion rates or the formation of massive seed black holes in the early universe. If massive black holes form early and power bright AGN, those AGN could masquerade as massive stellar populations in photometric observations, contributing to the population of apparently massive early galaxies. Looking at the range of proposed explanations, it is likely that multiple factors contribute to resolving the massive early galaxy problem, rather than a single explanation accounting for all observations. Some candidates are probably lower redshift interlopers. Some may have overestimated masses due to top-heavy IMFs or AGN contributions. And some may represent genuinely massive early galaxies that formed through more efficient processes than standard models predicted. Disentangling these cases requires extensive spectroscopic follow-up and detailed modeling, and this work is ongoing as JWST continues observing. The scientific process of proposing and testing explanations is how astronomy advances understanding, and the massive early galaxy discoveries from JWST are driving this process forward. Rather than being a crisis for cosmology, the observations are an opportunity to refine galaxy formation models and learn about physical processes in the early universe. The core physics of lambda CDM cosmology remains well supported by diverse observations, including the cosmic microwave background, Big Bang nucleosynthesis, and large-scale structure. So the massive galaxies are unlikely to overturn the entire cosmological framework. Instead, they are revealing that galaxy formation is more complex and varied than simplified models assumed. The tentative consensus emerging from ongoing research suggests that early star formation was probably more efficient than pre-JWST models predicted. That feedback may have been weaker or operated differently in the early universe, and that some early galaxy candidates include AGN contributions or our lower redshift objects. Revised galaxy formation models incorporating higher early efficiencies and weaker early feedback are being developed, and initial results show that such models can produce more massive early galaxies without violating fundamental constraints. The observations are driving the models to better match reality, which is exactly how science is supposed to work. Understanding the range of possible explanations provides context for appreciating that the massive early galaxies represent a scientific puzzle being actively investigated, rather than an unsolved mystery that threatens established physics. The puzzle is interesting precisely because it challenges assumptions and forces refinement of models, and solving it will improve our understanding of how galaxies formed in the early universe. The massive galaxy candidates are not isolated oddities, but part of a broader pattern of galaxies at high redshift that JWST is revealing. And examining this broader pattern helps clarify what the early universe was actually like. The massive galaxy candidates found in JWST observations are not isolated objects, but part of a larger population of high redshift galaxies that the telescope is revealing across multiple survey programs. Looking across the various deep field images that JWST has captured, you find dozens of galaxy candidates at redshifts above Z equals 10, and many of these show substantial stellar masses, even if not all reach the 100 billion solar mass level that creates the most severe timeline problems. The pattern emerging from these observations is that galaxies in the early universe appear more abundant and more massive than pre-JWST models predicted, suggesting that galaxy formation was more efficient or proceeded differently than theoretical frameworks assumed. The CEERS survey, which stands for Cosmic Evolution, Early Release Science, covered an area of the sky previously observed by Hubble and added JWST's infrared sensitivity to reveal fainter and more distant galaxies. Within the shears field, multiple galaxy candidates at redshifts from Z equals 10 to Z equals 16 were identified in the first data releases, and follow-up spectroscopy has confirmed several of these at high redshift, while identifying others as lower redshift interlopers. The confirmed high redshift population includes galaxies with stellar masses ranging from a few billion to tens of billions of solar masses, and the number density of such galaxies appears higher than models predicted for those redshifts. The GLASS survey, using JWST's near-infrared instruments to observe gravitationally lensed fields, where foreground galaxy clusters magnify background galaxies, found additional high redshift candidates, including some of the highest redshift galaxies currently known. Gravitational lensing allows detection of fainter objects than could be seen in blank fields, because the foreground cluster acts as a natural telescope, magnifying the background galaxies by factors of several to tens. One GLASS candidate, designated GLASS Z13, showed photometric colors consistent with redshift around Z equals 13 and appeared to be a compact but relatively massive galaxy for its epoch. Looking at the JDAS survey results, which stands for JWST Advanced Deep Extragalactic Survey, this program has identified numerous galaxies at redshifts from Z equals 9 to Z equals 14 through both photometric selection and spectroscopic confirmation. JADES obtained deep imaging in multiple filters, followed by spectroscopic observations of selected candidates, and the spectroscopic data confirmed galaxies at redshifts including Z equals 13.2 and Z equals 11.6, among others. The JDAS galaxies span a range of masses and show diverse morphologies, indicating that galaxy formation at high redshift produced varied outcomes rather than a single galaxy type. The abundance of high redshift galaxies in JWST observations can be quantified by the galaxy luminosity function, which describes how many galaxies exist at different brightness levels, and comparing the observed luminosity function to predictions reveals discrepancies. At redshifts around Z equals 10 to 12, the observed number of bright galaxies exceeds model predictions by factors of 3 to 10, depending on the exact redshift and luminosity range considered. This means that for every bright early galaxy that models predicted, JWST is finding 3 to 10 actual galaxies, suggesting that the models underestimated how efficiently early galaxies formed, or how quickly they grew to detectable luminosities. The number density of massive galaxies specifically also appears higher than predicted, and while precise statistics are still being compiled as surveys continue, preliminary estimates suggest that massive galaxies with stellar masses above 10 billion solar masses are about 5 to 10 times more abundant at Z greater than 10 than pre-JWST models predicted. This overabundance could indicate that star formation efficiency was higher, that dark matter halo masses were underestimated, or that some mechanism accelerated early galaxy growth. The statistics will improve as JWST surveys cover larger areas and obtain spectroscopic confirmation for more candidates. Looking at the distribution of galaxy properties at high redshift, you see a range of sizes, morphologies, stellar masses, and star formation rates, rather than a uniform population. Some high redshift galaxies are compact with sizes of only a few hundred parsecs, while others extend over several kiloparsecs. Some appear irregular and clumpy, consistent with early theoretical expectations, while others show surprising amounts of structure, including disk-like morphologies and central concentrations. The diversity suggests that galaxies at cosmic dawn were already experiencing various formation paths and evolutionary stages. Some high redshift galaxies show evidence of ongoing rapid star formation, with specific star formation rates defined as star formation rate divided by stellar mass, that are higher than typical values in the modern universe. These galaxies are building their stellar mass quickly and represent the vigorous, star-forming population expected in the early universe when gas supplies were abundant. Other high redshift galaxies show evidence of older stellar populations with ages of several hundred million years, suggesting that they formed most of their stars earlier and are now in a more quiescent phase. Finding quiescent galaxies at very high redshift is surprising because it implies extremely early and rapid star formation, followed by quenching. The clustering of high redshift galaxies provides information about the large-scale structure in the early universe, and preliminary studies of JWST data show that early galaxies are clustered in overdense regions, as expected if they formed in the peaks of the primordial density field. Some fields show multiple high redshift galaxies in close proximity, suggesting protoclusters or dense environments where galaxy formation was particularly active. These overdensities will eventually evolve into galaxy clusters and superclusters in later cosmic epochs, so observing them at high redshift provides a view of structure formation in action. Looking at the metallicity of high redshift galaxies, measured from emission line ratios in spectra, the values are generally low as expected for early cosmic times, when few previous stellar generations had enriched the gas with heavy elements. However, some early galaxies show surprisingly high metallicities given their age, indicating that they enriched their gas quickly through rapid star formation and supernova. The metallicity measurements provide constraints on star formation history and help distinguish between different formation scenarios, with rapid enrichment supporting scenarios involving intense early star formation. Some high redshift galaxies show evidence of active galactic nuclei through broad emission lines or high ionization features in their spectra, and the fraction of early galaxies hosting AGN appears substantial, though exact fractions are still being determined. The presence of AGN in early galaxies indicates that supermassive black holes formed quickly and grew to masses of millions to billions of solar masses by redshift Z equals 10 to 14. The coevolution of galaxies and supermassive black holes that is well established at lower redshifts appears to extend to the earliest cosmic epochs, with AGN feedback potentially playing a role in regulating early galaxy formation. The variability of some high redshift sources has been noted in repeated JWST observations, and variability can help distinguish between stellar-dominated galaxies and AGN, since AGN often vary in brightness on timescales of days to years, while stellar populations remain relatively constant. Monitoring programs that observe the same fields multiple times are revealing which early galaxy candidates are variable, and this information contributes to understanding the nature of the sources. Variable sources at high redshift may be AGN-dominated, or they might be extremely luminous individual stars, or transient events like supernovae magnified by gravitational lensing. Looking at the overall picture from multiple JWST surveys, the early universe revealed by the telescope is richer and more complex than anticipated before launch. Galaxies are present at the earliest times JWST can observe. They span a wide range of masses and properties, and they appear more abundant than models predicted, particularly at the high mass end. Some candidates remain controversial, with uncertain redshifts or debated interpretations, but a core population of confirmed high redshift galaxies is established and represents the earliest well-studied galaxy population. This population is teaching us about the first billion years of cosmic history and driving revisions to theoretical models. The pattern of discoveries across surveys strengthens the scientific case that something interesting is happening in early galaxy formation, and the consistency of finding more massive galaxies than expected across independent surveys reduces the likelihood that the results are flukes or systematic errors. The pattern demands explanation and has prompted the theoretical work exploring revised galaxy formation models with higher efficiencies, different feedback, or alternative formation pathways. The observations are also motivating additional JWST observation programs to expand the samples, obtain spectroscopy for more candidates, and study the detailed properties of early galaxies across cosmic time. Understanding the broader pattern of high redshift galaxies provides context for the massive galaxy candidates and shows that they are extreme examples within a more general population of surprisingly abundant and massive early galaxies. The entire population is informing revisions to galaxy formation models, and the massive candidates are the objects that push model constraints hardest. Exploring how models are being revised to accommodate the JWST observations reveals the scientific process in action as theory responds to unexpected data. The galaxy formation models that astronomers use to interpret observations and predict galaxy properties are being revised in light of the JWST discoveries, and these revisions involve adjusting parameters and incorporating processes that can produce more massive early galaxies without violating fundamental physics or cosmology. The standard framework for galaxy formation remains the lambda CDM cosmological model with hierarchical structure formation, where small dark matter halos collapse first and merge to form larger halos over time. This framework is well supported by numerous observations and is not being abandoned, but the details of how baryonic matter behaves within dark matter halos are being reconsidered. One key parameter being revised is star formation efficiency, which describes what fraction of gas falling into a dark matter halo ultimately forms stars. Previous models assumed relatively low star formation efficiencies of 10 to 20%, based on observations of galaxies at lower redshifts and theoretical arguments about feedback limiting star formation. If early galaxies had higher star formation efficiencies of 30 to 50% or more, they could build up stellar mass faster without requiring higher gas infall rates. Higher efficiency might result from different gas conditions in the metal-poor early universe, or from denser environments that make gas cooling and collapse more efficient. Feedback processes are another area where models are being adjusted, and reducing the strength of feedback in the early universe allows more gas to remain in galaxies and form stars. Supernova feedback depends on how efficiently the explosion energy couples to the surrounding gas and drives outflows, and this coupling could be less efficient in the high-density environments of early dark matter halos. If supernovae explode into denser surroundings, the energy disperses into a smaller mass of gas and produces less dramatic outflows, allowing more gas to remain gravitationally bound to the galaxy. Weaker feedback increases the net star formation efficiency by reducing gas losses. Looking at stellar feedback more broadly, radiation pressure from massive stars and stellar winds contribute to regulating star formation by heating gas and preventing its collapse. In metal-poor environments characteristic of the early universe, stellar winds are weaker because wind driving depends partly on metals in stellar atmospheres that absorb radiation and transfer momentum to the wind. Weaker stellar winds mean less mass loss from stars and less energy injection into the surrounding gas, which again permits higher star formation efficiencies. Models incorporating these metallicity-dependent feedback effects predict faster, early galaxy growth. Active galactic nucleus feedback is also being considered in revised models, though its role in the early universe is complex. AGN can inject enormous amounts of energy into galaxies through jets, winds, and radiation, and this energy can heat gas and suppress star formation. However, AGN might also trigger star formation in some circumstances by compressing gas, and the net effect depends on details of how AGN interact with their host galaxies. Observations showing AGN in some early massive galaxies suggest that black hole growth and galaxy growth occurred together, and models are exploring how to incorporate this coevolution at high redshifts. The stellar initial mass function is another parameter that could differ in the early universe from the IMF observed locally, and some revised models explore top-heavy IMFs where a larger fraction of stars form at high masses. A top-heavy IMF produces more light per unit stellar mass because massive stars are very luminous, and this would mean that the bright early galaxies observed by JWST could have lower stellar masses than estimated using standard IMFs. The stellar masses might be tens of billions rather than hundreds of billions of solar masses, which would make them easier to explain within available time constraints. However, top-heavy IMFs also produce more supernovae and more feedback, which creates counteracting effects. Looking at dark matter halo growth, some revised models suggest that the most massive halos at high redshift might be more massive or more abundant than standard calculations predict, if small-scale density fluctuations were larger than extrapolated from large-scale measurements. The cosmic microwave background constrains density fluctuations on scales of tens to hundreds of megaparsecs. But smaller scales are less well constrained, and it is possible that fluctuations on galaxy scales were enhanced relative to simple power law extrapolations. Enhanced small-scale power would produce more massive halos earlier, providing deeper potential wells and higher gas inflow rates to feed faster galaxy growth. Direct collapse formation pathways are being explored in some models as an alternative to gradual hierarchical assembly. And these scenarios involve rapid collapse of large gas clouds directly into massive galaxies or massive black holes. For direct collapse to occur without fragmenting into many small objects, certain conditions must be met, including high gas temperatures that prevent cooling and collapse on small scales, or strong turbulence that suppresses fragmentation. Such conditions might exist in the early universe under special circumstances, and if direct collapse is possible, it could produce massive objects more quickly than hierarchical assembly. The merger rates between galaxies in the early universe might have been underestimated in previous models, and the denser environment at high redshift naturally leads to more frequent encounters between galaxies. If mergers happened more often than models predicted, galaxies could grow faster by accreting the stellar mass from merger partners. Major mergers between similar mass galaxies can double the stellar mass in a single event, and a sequence of mergers over a few 100 million years could build up substantial mass. Models are exploring whether realistic merger rates at high redshift can account for the massive early galaxies observed by JWST. Looking at the overall approach to revising models, the process involves identifying which parameter changes or physical processes can produce more massive early galaxies while remaining consistent with other observations and physical constraints. The revised models must still match observations at lower redshifts, where data is abundant and well understood, and they must not violate constraints from the cosmic microwave background, Big Bang nucleosynthesis, or large-scale structure. The goal is to find minimal modifications that explain the JWST observations while maintaining agreement with the broad range of cosmological data. Preliminary results from revised models show that increasing star formation efficiency to 30 to 40% and reducing feedback strength by factors of 2 to 3 can produce galaxies at Z equals 10, with stellar masses around 50 to 100 billion solar masses. These masses approach the observed values for the most massive JWST candidates, suggesting that the models can accommodate the observations without requiring exotic new physics. The revised models predict more massive early galaxies than pre-JWST models, but still produce a hierarchical buildup, where the most massive galaxies are rare at high redshift. The revised models also predict that massive early galaxies should have high specific star formation rates because they are building their mass rapidly, and this prediction can be tested against JWST spectroscopic observations that measure star formation rates. If observed specific star formation rates match model predictions, this supports the revised formation scenarios. If observed rates are lower than predicted, it might indicate that the galaxies formed even earlier and have already quenched their star formation, which would pose additional challenges. Ongoing comparisons between model predictions and observations are testing these scenarios. Looking at the broader implications of model revisions, the changes being made are refinements to galaxy formation prescriptions within the standard cosmological framework, rather than overturns of fundamental physics. The lambda CDM model itself is not being questioned by the massive early galaxies, and the basic picture of dark matter halos forming hierarchically from initial density fluctuations remains valid. What is changing is our understanding of how efficiently gas turns into stars in the early universe and how feedback processes operate under early cosmic conditions. These are important refinements that improve the models, but do not represent a crisis for cosmology. The process of revising models in response to new observations is normal in science, and it demonstrates that theoretical frameworks are being tested and improved as better data becomes available. The JWST observations are providing unprecedented views of the early universe, and it is not surprising that pre-JWST models, which were based on limited high redshift data, need adjustment now that detailed observations are available. The revisions are making models more accurate and predictive, which is exactly what should happen when new data challenges previous assumptions. Understanding that models are being successfully revised to accommodate JWST observations helps contextualize the massive early galaxy discoveries as scientific progress rather than crisis. The observations surprised astronomers by revealing that galaxy formation was more efficient than expected, and this surprise is driving theoretical advances. The scientific community is actively working through the observations, proposing and testing explanations, and refining models, which is the normal process of advancing knowledge. The journey from surprise to understanding is ongoing, and additional observations continue to inform the process. The process of understanding the massive early galaxies continues through ongoing observations with JWST and other telescopes, and these observations are providing the detailed data needed to distinguish between different explanations and refine models. Spectroscopic observations are particularly important because spectra confirm redshifts and reveal information about stellar populations, star formation rates, metallicities, and the presence of active galactic nuclei that photometric observations alone cannot provide. JWST's NIR-SPEC instrument is capable of obtaining spectra of high redshift galaxies, and spectroscopic programs are targeting massive early galaxy candidates to characterize their properties. Looking at the spectroscopic results obtained so far for massive early galaxy candidates, some objects have confirmed spectroscopic redshifts that place them firmly at Z greater than 10, while others have been identified as lower redshift galaxies that mimicked high redshift colors through dust reddening or other effects. The confirmed high redshift population includes galaxies with stellar masses that appear genuinely large for their cosmic epoch, supporting the conclusion that massive early galaxies exist and need to be explained. The spectroscopic data also reveals emission lines from hydrogen, oxygen, and other elements that provide information about the physical conditions in these galaxies. Emission line ratios measured from spectra allow determination of gas metallicity, which indicates how much heavy element enrichment has occurred through previous stellar generations. The metallicities of confirmed massive early galaxies are generally low compared to local galaxies, as expected for early cosmic times, but some show higher metallicities than anticipated for such young systems. High metallicity at early times suggests rapid chemical enrichment through intense star formation, which is consistent with the high star formation rates needed to build up the observed stellar masses quickly. The metallicity measurements support scenarios involving vigorous early star formation. Star formation rates can be estimated from emission line strengths, particularly the hydrogen alpha line that traces ionization by young massive stars, and these measurements reveal how rapidly the galaxies are forming new stars at the time of observation. Some massive early galaxies show high star formation rates of hundreds to thousands of solar masses per year, confirming that they are building stellar mass rapidly. Others show lower current star formation rates, despite having large stellar masses, suggesting that they formed most of their stars earlier and are now in a more quiescent phase. The range of star formation rates indicates that early massive galaxies include both actively star-forming and more passive populations. Looking at active galactic nucleus signatures in spectra, broad emission lines indicating gas moving at high velocities near a supermassive black hole are detected in some early massive galaxies. The presence of AGN means that part of the observed light comes from black hole accretion rather than stars, which complicates stellar mass estimates for those objects. Distinguishing stellar and AGN contributions requires detailed spectral modeling, and ongoing work is refining mass estimates by accounting for AGN light. For galaxies with strong AGN signatures, the stellar masses may be lower than initial photometric estimates suggested, reducing the severity of the timeline problem. High-resolution imaging from JWST allows detailed study of galaxy morphology and examining the spatial distribution of light in massive early galaxies reveals structural information. Some galaxies appear compact, with all their light concentrated in a small region, while others show extended disks or multiple components. Compact morphology is consistent with rapid central star formation building up mass in a dense core, while extended morphology suggests that gas has settled into a disk structure. The morphological diversity indicates that early massive galaxies reached their masses through different formation paths. The stellar populations in massive early galaxies can be studied through spectral features that reveal stellar ages, and some spectra show evidence of both young and old stellar populations coexisting in the same galaxy. The presence of old stars requires that star formation began very early, potentially within the first 100 to 150 million years after the Big Bang, to allow enough time for stars to age. Finding old stellar populations in galaxies observed at redshift Z equals 10 to 13 pushes the onset of star formation to very early times and constrains models of the first galaxy formation. Looking at the rest frame ultraviolet properties of early galaxies, observations in this wavelength range trace young massive stars and provide information about recent star formation. JWST observes rest frame ultraviolet light that has been redshifted into the near-infrared, and analyzing the ultraviolet spectral slopes and features reveals the intensity of star formation and the escape of ionizing photons. Galaxies with steep ultraviolet slopes show evidence of strong dust attenuation, while galaxies with blue ultraviolet slopes indicate relatively dust-free star formation. The ultraviolet properties complement the rest frame optical and infrared data to build a complete picture. Variability studies comparing images taken at different times can identify active galactic nuclei through brightness changes, and some early galaxy candidates show variability consistent with AGN. Variable sources are being flagged for detailed spectroscopic follow-up to confirm their nature, and understanding the AGN contribution to early massive galaxies is important for accurate stellar mass estimates. Non-variable sources are more likely to be dominated by stellar light, making their mass estimates more reliable. Ongoing monitoring programs will expand the sample of objects with variability data. Gravitational lensing observations are targeting massive early galaxies to obtain magnified views that reveal internal structure, and lensed galaxies appear distorted into arcs or multiple images that can be modeled to reconstruct the source galaxy properties. The magnification from lensing allows detection of fainter structures and smaller spatial scales than possible in unlensed observations, and this detail helps constrain galaxy formation models. Some of the highest redshift galaxies known are lensed objects, where the magnification makes them detectable despite their intrinsic faintness. Looking at the overall sample of massive early galaxies with detailed follow-up data, a picture is emerging of a diverse population with varied properties. Some candidates have been ruled out as high redshift objects. Some have confirmed high redshifts but lower masses than initially estimated, and some remain as genuinely massive early galaxies that challenge models. The population is smaller than initial photometric samples suggested, but it is non-zero and requires explanation. The refined sample provides clearer targets for theoretical modeling and helps focus efforts on explaining the most robust cases. Statistical studies combining data from multiple JWST surveys are quantifying the abundance of massive early galaxies more precisely, and these statistics constrain models by showing how common such objects are. If massive early galaxies were extremely rare, they might represent statistical flukes in the tail of the distribution, where occasional objects reach high masses through chance sequences of mergers or unusual conditions. If they are relatively common, the formation mechanisms must be more generally applicable and represent standard processes operating efficiently. Current statistics suggest that massive early galaxies are uncommon, but not extraordinarily rare, appearing in significant numbers when large volumes are surveyed. The comparison between observations at different redshifts reveals how galaxy properties evolve over the first billion years of cosmic history, and this evolution provides additional constraints on models. Observations at z equals 8, 10, 12, and 14 show how galaxy masses, sizes, and star formation rates change with time, and models must reproduce these trends. The evolution from first galaxies at z equals 15 to 20 down to more mature systems at z equals 8 to 10 traces the buildup of cosmic structure and tests whether models can match the observed pace of evolution. Looking at the future of observational studies, ongoing and planned JWST programs will expand the sample sizes and obtain deeper observations that reveal fainter galaxies. Spectroscopic campaigns will confirm more high redshift candidates and characterize their properties in detail, reducing uncertainties and building robust samples for statistical analysis. Coordination with other observatories, including ground-based telescopes and other space telescopes, will provide complementary data at different wavelengths. The accumulation of data over JWST's mission lifetime will progressively refine our understanding of early galaxy formation. The iterative process of observation, analysis, interpretation, and model revision is central to the scientific method, and the massive early galaxy discoveries exemplify this process. Initial JWST observations revealed surprising objects. Follow-up studies confirmed some surprises and resolved others as less extreme. Theoretical models were revised to accommodate confirmed observations, and additional observations continue to test the revised models. This cycle drives progress toward understanding how galaxies formed in the early universe, and each cycle brings theoretical predictions and observations into closer alignment. Understanding that the scientific investigation of massive early galaxies is ongoing and productive helps contextualize the discoveries as part of normal scientific progress. The observations are not inexplicable anomalies, but rather clues about how galaxy formation operated under early universe conditions. And astronomers are successfully using those clues to refine theoretical models. The process of discovery and understanding takes time and requires accumulating evidence, and JWST is providing that evidence while astronomers work through its implications. The journey from surprising observation to complete understanding is inherently gradual, and we are in the middle of that journey. The massive early galaxies discovered by the James Webb Space Telescope fit into the larger story of our evolving understanding of the early universe. And they represent one chapter in the ongoing exploration of cosmic dawn and the epoch when the first stars and galaxies formed. JWST was specifically designed to observe this epoch, and the discoveries of massive early galaxies, while surprising in their details, are exactly the kind of result the telescope was built to obtain. The mission's purpose is to reveal what the early universe was actually like, rather than confirming predictions, and surprises are part of the discovery process that advances scientific knowledge. Looking at the broader context of JWST's mission, the telescope's capabilities enable observations across a wide range of science topics, including exoplanet atmospheres, stellar formation regions, galaxies at all cosmic epochs, and the early universe. The early universe observations are a primary science driver, and JWST's infrared sensitivity and large mirror were optimized for detecting the highly redshifted light from the first galaxies. The telescope is performing as designed and delivering data quality that exceeds pre-launch expectations, allowing detection of fainter and more distant objects than anticipated. The massive early galaxies are part of this success story. The Lambda CDM cosmological model remains the foundation for understanding cosmic structure formation, and the massive early galaxy discoveries do not undermine this foundation. The model's predictions for the cosmic microwave background, the abundances of light elements from Big Bang nucleosynthesis, and the large-scale distribution of galaxies all match observations with remarkable precision. The model correctly predicts the overall framework of hierarchical structure formation, where small fluctuations grow through gravitational collapse to form the cosmic web. The massive early galaxies challenge specific assumptions about galaxy formation efficiency, rather than the underlying cosmological framework. Understanding that galaxy formation models are more uncertain than the underlying cosmology helps contextualize why revisions are needed and why such revisions are scientifically acceptable. Cosmology deals with the universe's overall properties and evolution, which are governed by well-tested physics, including general relativity and thermodynamics. Galaxy formation involves more complex astrophysics, including gas dynamics, star formation, stellar feedback, black hole growth, and magnetic fields. And modeling these processes requires simplifications and assumptions. The assumptions are testable through observations, and JWST is providing tests that reveal where assumptions need revision. Looking at the specific revisions being made to galaxy formation models, the changes involve increasing star formation efficiency in the early universe and reducing feedback strength compared to previous assumptions. These changes are plausible because early universe conditions differed from later conditions in ways that could affect efficiency and feedback. Gas in the early universe had lower metallicity, higher density, and experienced stronger cosmic microwave background radiation, all of which could influence how efficiently gas-cooled and formed stars and how strongly feedback coupled to the gas. The revised models incorporate these effects more carefully. The timeline constraints that initially made massive early galaxies seem impossible are being relaxed through higher efficiencies and weaker feedback. And the revised models show that forming 50 to 100 billion solar masses by redshift Z equals 10 is achievable under reasonable assumptions. The required star formation rates remain high at hundreds of millions of solar masses per year, but sustained over 300 million years, such rates can build up the observed masses. The rates are not impossible in an absolute sense, but rather represent the upper end of what physics allows, indicating that early massive galaxies formed under near-optimal conditions for star formation. The role of active galactic nuclei in early massive galaxies is still being determined, and the detection of AGN in some candidates indicates that supermassive black holes formed early and contributed to the observed light. Understanding the coevolution of galaxies and black holes in the early universe is a research frontier, and JWST observations are revealing that this coevolution extends to the earliest cosmic epochs. The interplay between black hole growth, AGN feedback, and stellar mass assembly in early galaxies will be a topic of study for years as more data accumulates and models become more sophisticated. Looking at what the massive early galaxies teach us about cosmic dawn, they reveal that the first galaxies assembled their mass quickly and efficiently, transforming primordial gas into stars on timescales of hundreds of millions of years. This rapid assembly created structured galaxies with substantial stellar populations by the time the universe was only a few % of its current age. The efficiency of early star formation suggests that the conditions in the early universe were conducive to galaxy formation, despite the lack of heavy elements and the challenges of cooling primordial gas. The massive early galaxies also inform our understanding of cosmic reionization, which is the process by which ultraviolet light from the first stars and galaxies ionized the neutral hydrogen that filled the universe after recombination. Reionization occurred between redshift Z equals 6 and Z equals 20 based on various observational constraints, and the massive early galaxies observed by JWST at Z equals 10 to 15 existed during this epoch. Their ultraviolet light contributed to reionizing the intergalactic medium, and understanding their abundance and properties helps model the reionization process. More massive galaxies produce more ionizing photons and have greater impact on reionization. The scientific process, exemplified by the massive early galaxy discoveries, is how astronomy progresses from limited knowledge to deeper understanding through the cycle of observation, hypothesis, prediction, and testing. Before JWST, our knowledge of the early universe was limited by the capabilities of available telescopes, and models were based on extrapolating from lower redshift observations and theoretical principles. JWST has provided direct observations of the early universe that test those extrapolations, and the observations reveal aspects that models did not anticipate. This is exactly what new observational capabilities should do. Looking at the broader implications for our understanding of galaxy evolution, the JWST discoveries show that galaxies began forming earlier and grew faster than previously thought, which compresses the timeline of cosmic structure formation. The universe transitioned from a dark, featureless state after recombination to a state filled with galaxies and reionized gas more quickly than pre-JWST models suggested. This faster evolution means that the universe became complex and structured earlier in its history, and later epochs inherit a richer starting point, with more evolved galaxies already in place by redshift Z equals 6 to 8. The discoveries also have implications for understanding our own Milky Way galaxy's formation history, as the processes that formed early massive galaxies are related to the processes that formed the progenitors of the Milky Way. The Milky Way assembled over billions of years through mergers and gas accretion, and some of its stars formed in small galaxies that later merged to become part of the larger system. Understanding how the first galaxies formed and grew provides context for interpreting the fossil record preserved in the Milky Way's stellar populations, and for understanding how galaxies like ours came to exist. The ongoing nature of JWST's mission means that the story of massive early galaxies is still being written, and future observations will continue to refine our understanding. The telescope has many years of operation ahead, and each year will bring deeper observations, larger samples, and more detailed characterization of early galaxies. The accumulation of data will progressively reduce uncertainties and test model predictions, allowing astronomers to distinguish between different formation scenarios and converge on the correct explanation for how massive galaxies formed so early. Looking ahead, the next generation of observatories, including future space telescopes and extremely large ground-based telescopes, will build on JWST's discoveries and push observations to even higher redshifts and fainter objects. These future observations will reveal the very first galaxies forming at redshifts beyond Z equals 20, and will trace the evolution from those first small systems to the massive galaxies observed by JWST at Z equals 10 to 15. The complete story of galaxy formation, from the first stars to the present day, will emerge from this multi-generational observational program. The massive early galaxies discovered by JWST represent a genuine scientific surprise that has enriched our understanding of the early universe, rather than creating a crisis for cosmology. The galaxies are more massive and more abundant than models predicted, and this discrepancy has driven revisions to galaxy formation theory that improve the models and bring them into agreement with observations. The process demonstrates science working as it should, with observations challenging theory and theory adapting to explain observations. The universe has revealed itself to be more interesting and complex than we anticipated, which is the outcome we should hope for from new observations. Standing here, looking at one of these massive early galaxies through JWST's infrared vision, you see an object that exists at the edge of our observational reach. A galaxy from cosmic dawn whose light has traveled for over 13 billion years to reach the telescope. The galaxy appears bright and structured despite its extreme distance, and it represents one of the first major systems to form after the Big Bang. What seemed impossible at first has become an opportunity for learning, and the galaxy is teaching us that the early universe was more efficient at forming structure than we previously understood. The journey through the science of massive early galaxies has taken you from direct observation of these remarkable objects through understanding the measurements that reveal their properties, to exploring the challenges they pose and the solutions being developed. Along the way, you have seen science in action, the iterative process of observation and interpretation that gradually builds knowledge. The massive early galaxies are no longer impossible, but rather understood as the products of efficient early star formation in a young, dense universe. And this understanding represents progress in our cosmic story. The early universe continues to hold mysteries that JWST and future telescopes will gradually illuminate, and each mystery solved reveals new questions to explore. The massive early galaxies represent one set of questions being actively investigated, and their resolution will enable asking deeper questions about the first stars, the first black holes, and the transition from a dark universe to one filled with light. The process of cosmic discovery is ongoing, and we are privileged to witness this chapter as it unfolds through JWST's remarkable observations.